Welcome to this deep dive. You've shared some really fascinating material from IFI about designing houses that, well, not only keep you comfortable, but actually produce more energy for heating and cooling than they use over a year.
Hmm.
It's a pretty bold idea, and we're excited to really dig into how that's even possible.
Yeah.
Your goal, as we understand it, is to get a clear picture of the core principles behind achieving this energy surplus. The IFI article introduces their Aladdin software as a tool to help students explore these concepts, and we'll be using their insights as our guide.
It's a truly transformative concept.
Mm,
For so long, buildings have just been seen as energy sinks.
right.
The idea that they could become net energy producers,
Yeah.
well, it has profound implications for sustainability and, frankly, how we live.
Mm.
And the fact that IFI is using a tool like Aladdin to make these complex interactions understandable is a significant step forward.
Absolutely. And for you, our listener, who's keen on getting a thorough grasp of intricate subjects without getting bogged down, Aladdin sounds like an incredibly useful way to visualize some pretty complex energy dynamics.
Hmm.
IFI mentions it even incorporates weather data from almost 1,000 locations around the globe, so it's all grounded in real-world conditions, which seems essential.
Oh, that real-world grounding is critical.
Yeah,
Definitely. What works in, say, the sunny Southwest is going to be very different from what's effective in the colder Northeast, right?
sure.
So the ability to simulate performance based on actual climate data adds a layer of practicality that's just invaluable.
Okay, so let's start by trying to get a handle on some of the fundamentals that IFI lays out. They talk about how heat moves through a building, the walls, roof, windows, doors, all that.
Uh-huh.
They don't get into really complicated equations, thankfully, but they explain that the rate of heat flow is influenced by a few key things. Like imagine a window on a cold day. The bigger the window, obviously the more surface area there is for heat to escape. And naturally, the bigger the temperature difference between the cozy inside and the chilly outside, the faster that heat will try to get out. Makes sense. Then there's this idea of how easily, or I guess how stubbornly, a material allows heat to pass through it. That's where the U value comes in.
Ah, yes.
A higher U value basically means heat can flow through that material more readily, like wearing a thin sweater on a winter day. Conversely,
Exactly. Conversely, a lower U value indicates a material that's more resistant to heat flow, like a thick insulated coat. Think of it in terms of conductance, how well something conducts heat. A low U value means low thermal conductance.
right. Okay. And IFI also mentions the R value. Is that the same thing
Yeah,
or related?
not exactly the same. No, it's more the flip side of the same coin. While the U value tells us how easily heat gets through something,
Mm-hmm.
the R value tells us how well a material resists heat flow. So a high R value means the material is a good insulator,
Mm.
doing a great job of keeping heat where you want it inside in winter, outside in summer. It's about thermal resistance. IFI points out that in the U.S. anyway, you'll often see U values used for windows and doors, while R values are more common for things like wall and roof insulation.
Ah, that makes sense. So when we're aiming for an Energy Plus house, we generally want lower U values for our windows and higher R values for our walls and roof, right? To minimize unwanted heat loss and gain.
Precisely. Yep. That's a fundamental principle in reducing the energy demand for heating and cooling in the first place.
Yeah.
You got to stop the leaks, essentially.
Now, IFI also makes it clear that just understanding how heat moves through the structure itself isn't the whole story. They bring up solar radiation, which sounds like a whole other factor we need to consider.
Absolutely. Solar radiation is, well, it's the energy coming directly from the sun. When it hits a building, some of that energy is absorbed and turned into heat. And the amount absorbed depends on things like the angle of the sun, which changes throughout the day and the year. The orientation of the building's surfaces, south-facing walls, get more direct sun, for example, and even the color and properties of materials themselves. A dark roof will absorb more solar energy than a light-colored one.
Hmm.
Aladdin's ability to simulate and even visualize the solar intensity on different parts of the house is incredibly helpful for understanding its impact on our energy needs.
Yes, seeing those heat flow visualizations and the solar intensity maps that Aladdin can generate really helps to make that abstract concept more concrete. You can immediately see why, say, a big south-facing window could be fantastic in the winter for soaking up solar heat
Passive heating.
and warming the place naturally, but could become a major source of overheating in the summer months.
Exactly. What's fascinating here is the dynamic interplay between how much heat is lost or gained through the building's skin, the walls, roof, windows, and how much solar energy is either welcomed in or rejected. These two factors are the primary drivers of a building's heating and cooling requirements.
Okay. The IFI article then transitions into the engineering analysis side of things, emphasizing the need for actual numbers, quantitative results to understand the impact.
Right, got to crunch the numbers.
Aladdin can generate these graphs showing the projected annual energy consumption for heating and cooling. It gives you a really clear picture of those seasonal trends, the peak in heating demand during the winter months, the rise in cooling needs during the summer.
And that quantitative analysis is absolutely crucial for making informed design choices. It allows you to see, in black and white, the effect of different interventions. If you add more insulation, how much does it reduce your heating load?
Uh-huh.
If you choose different windows, what's the impact on your cooling needs? That's the real power of simulation.
This sets the stage perfectly for the two main strategies IFI explores for actually achieving that energy surplus we talked about at the beginning: active solar design and passive solar design. Let's start with active solar. In this context, it sounds like it primarily refers to installing photovoltaic solar panels, right, to generate electricity.
Exactly. Active solar systems involve using technology, like solar panels, to actively convert sunlight into usable energy, in this case, electricity. IFI even gives a specific example, mentioning the SunPower SPR X21335 solar panel, noting its efficiency rating and power output.
Okay.
They then describe a simulation where they fit an array of 35 of these panels onto the south-facing roof of a sample house located near Boston.
And what were the results? I imagine that generated a significant amount of electricity.
It did. It generated a significant amount, no doubt. However, the simulation showed that even with that substantial solar array, the house didn't quite reach a net energy surplus for heating and cooling over the entire year, particularly during the colder winter months when heating demands are high and, well, solar energy production could be lower due to shorter days and less intense sunlight.
Ah, that's a key insight, isn't it? It highlights that just generating a lot of electricity doesn't automatically solve the energy balance for heating and cooling.
Absolutely. It really underscores that achieving an energy plus home isn't solely about maximizing energy generation. It also requires a significant focus on minimizing energy consumption in the first place. You have to tackle both sides.
Interestingly, IFI also points out a kind of secondary effect of the solar panels themselves. They can slightly increase the heating load and decrease the cooling load by shading the roof.
Yeah.
It's like they're providing a bit of extra shade in the summer, which is good for cooling, but they're also preventing some of that direct solar gain on the roof in the winter, which could have contributed to passive heating.
That's a really astute observation from IFI. It highlights the interconnectedness of all these design elements. Even something as seemingly straightforward as adding solar panels can have nuanced effects on other aspects of the building's energy performance.
Yeah.
It really reinforces the value of that comprehensive simulation that Aladdin offers, allowing you to see these subtle but potentially important trade-offs.
Let's move on to passive solar design then. This sounds like it's all about using the fundamental design of the building itself to manage solar energy without relying on active technologies like panels.
That's the idea.
One technique IFI discusses is carefully choosing windows with a specific solar heat gain coefficient, or SHGC. Can you break down what that means for us?
Certainly, the solar heat gain coefficient, or SHGC, is a measure of how much of the sun's energy that hits a window actually ends up as heat inside the building. A lower SHGC means that less solar heat is transmitted through the glass. So by strategically selecting windows with a lower SHGC, especially on the east and west-facing sides of the house, which tend to get a lot of direct sunlight during the hottest parts of the day.
Right, morning and afternoon sun.
Exactly. You can significantly reduce unwanted solar heat gain in the summer, which in turn reduces your cooling needs.
And IFI found that applying this strategy using windows with a lower SHGC on the west and east sides of their model house actually resulted in a net energy saving over the year, even though it slightly increased the need for heating during the winter. That's a fascinating trade-off.
It is quite interesting, yeah. In many climates, the extended period of warmer weather and intense sun means that reducing solar gain during those months can have a more substantial impact on overall energy consumption than a marginal increase in heating demand during the shorter, cooler periods. However, as IFI points out, this strategy wasn't beneficial for the south and north-facing windows.
Right, because those south-facing windows can be valuable in the winter for capturing that lower-angle sunlight and providing passive heating, We want that heat then.
Precisely.
And the north-facing windows generally don't receive much direct sun anyway, so adjusting their SHGC wouldn't make a significant difference. It really underscores the importance of understanding the sun's path and intensity on different sides of the house throughout the year.
Exactly. It's about tailoring the design to the specific orientation and solar exposure of each facade. A one-size-fits-all approach just won't be as effective as a more nuanced strategy.
Another passive design element that IFI highlights is something surprisingly simple: planting trees around the house.
Ah, yes. Trees.
Their simulations showed that strategically placed trees can significantly reduce the cooling load in the summer by providing shade.
Trees are a fantastic example of a low-tech, sustainable solution with multiple benefits. They act as natural sunshades, preventing direct sunlight from hitting the building's walls and roof, which in turn reduces the amount of heat absorbed and helps keep the interior cooler.
Makes sense.
And as IFI notes, if you choose the right types of trees, like deciduous ones, and plant them thoughtfully, they don't necessarily have to negatively impact the productivity of solar panels on the roof.
Oh, right, because they lose their leaves in winter?
Exactly. They lose their leaves in the winter, allowing more sunlight to reach the roof, when that solar gain might actually be more desirable for heating.
It's a beautiful example of how nature can work in harmony with building design to enhance energy efficiency. So finally, IFI delves into thermal solutions, which essentially comes down to improving the insulation of the house.
The building envelope.
They discuss increasing the R values of the roof and walls and decreasing the U value of the windows. We touched on these earlier, but how do these improvements contribute to achieving an energy surplus?
Well, by significantly increasing the R value of the walls and roof, you're essentially making the building envelope much, much more resistant to the flow of heat. Think of it like putting on a much thicker, more effective thermal blanket around the house. This means less heat will escape in the winter, reducing the need for your heating system to work as hard, and less heat will enter in the summer, lessening the burden on your air conditioning.
Right.
Similarly, by decreasing the U value of the windows, making them less conductive to heat, you're minimizing another major pathway for heat loss and gain. Better windows are key.
So it's like creating a really well-sealed and insulated box that minimizes the exchange of heat with the outside environment, a thermos almost.
Exactly. A thermos is a great analogy.
Yeah.
IFI mentions using things like triple pane windows with a very low U value and achieving high R values in the walls and roof levels that go beyond the minimum requirements in many building codes. Super insulation, basically.
Wow.
And it was through this combination, incorporating active solar with the panels, employing passive solar strategies like smart window choices and strategic landscaping, and significantly improving the thermal performance through enhanced insulation, that their example house was finally able to achieve an energy surplus over the course of a year for heating and cooling.
So it sounds like it's this integrated approach where all these different elements work together: the solar panels generating clean electricity, the passive design features minimizing unwanted solar heat gain and maximizing beneficial solar gain, and the high levels of insulation reducing overall heat exchange that ultimately tips the balance towards the house producing more energy than it consumes for comfort.
That's the key takeaway from IFI's work, I think. It's not about finding one single magic bullet, but rather about understanding the complex interactions between all these different design parameters and optimizing them holistically.
Right.
Aladdin, the software they developed, seems like a powerful tool for exploring these trade-offs and arriving at truly energy efficient and potentially energy positive designs.
Well, as you can see from this deep dive into the IFI article, designing an Energy Plus house is a really fascinating and multifaceted challenge. It requires a solid understanding of some fundamental principles of physics, like how heat moves and how solar energy interacts with buildings. We've explored how U values and R values describe a material's ability to transmit or resist heat, the significant impact of solar radiation, and a range of solutions, from installing high-efficiency solar panels to making smart choices about windows and even planting trees. It's quite remarkable how all these pieces fit together to influence a building's overall energy performance.
I think what's particularly valuable about IFI's work and the way they're using the Aladdin software is that it really emphasizes the importance of thinking about a building as a complete system.
Yeah.
It's not just about adding a bit of insulation here or installing a few solar panels there. It's about understanding how all the components interact and making informed decisions based on data and simulation to achieve truly sustainable and energy-positive outcomes.
Absolutely. And the whole concept of an energy plus house really challenges us to shift our perspective on buildings, doesn't it? Instead of just seeing them as consumers of energy, we can start to envision them as potential contributors to a more sustainable energy future. It opens up so many interesting questions about how these strategies might be adapted for different climates, what the economic implications of these technologies are, and what exciting innovations in building materials and renewable energy are still on the horizon.
It certainly does. It's a field that's constantly evolving, and IFI's work provides a valuable framework for understanding the current state of the art and the potential for future advancements.
Thank you for joining us on this deep dive into the fascinating work of IFI and the principles behind designing Energy Plus houses. We hope this exploration has provided you with some valuable insights and maybe sparked your curiosity to learn more about the exciting possibilities of energy efficient building design.